Hello everyone, I am Zudi Kakde. I am final year engineering student from Walchand Institute of Technology, Solapur at Department of Information Technology. Today, we will learn in virtual lab experiment of IIT Hyderabad. In this, we will perform under cryptography lab experiment number 7, that is symmetric key encryption standards AES. So in this experiment, we have to encrypt long messages using various modes of operation wherein block cipher. Talking about the theory, we'll learn a brief about what is advanced encryption standard. It is clear replacement for DES, whereas DES is a digital encryption standard. DES has key size too small. Can use triple DES, but it is slow and has small blocks. AES Cipher is also well known as Rijndael. Rijndael was selected as AES in October 2000, which was designed by John Raymond and Vincent Dim in Belgium. It has 128, 192, 256-bit keys. It is an iterative rather than Festal cipher. Processes data as a block of 4 columns of 4 bytes. Operates on entire data block in every round, designed to be resistant against known attacks and has a speed and code compactness on many CPUs, and well, it is in simplest to understand. So AES encrypts messages in blocks of 128 bits. AES allows 3 different lengths, that is 128, 192 and 256 bits. The number of rounds in encryption and decryption is dependent on the key length, where 128 bit is of 10 rounds, 192 bit is of 12 rounds, 256 bit is of 14 rounds. So in this, the data block viewed as 4x4 table of bytes, which is to be considered as 4 into 4 matrices. Such table is called as current state. The key is expanded to the array of words. It has 10 rounds in which state following transformation. The first and last round are a little different. So we will go to the next page. So we have here a clear diagrammatical representation where we have converting plain text to the ciphertext. So in the round 1 we have substituted bytes, shift rows, mix columns, add round key. So basically we have considered here 128 bits, and which I have told earlier it has 10 rounds. So this thing is gonna repeat for 10 times. So round 1 to round 9 all the steps are same, but in round we consider it as only 3 steps: substitute bytes, shift rows, add round key, and we get the cipher. For decryptions, we have to do the reverse method to get a plain text. We will go the steps. Byte substitution. It is a simple substitution of each byte. Uses one S box of 16 into 16 bytes containing a permutation of all 256 8-bit values. Each byte of state is replaced by byte index by row and column, where Xbox is on board. Xbox constructed using a simple math formula using a non-linear function 1 by x. So basically this is the representation where we have considered a 4 by 4 matrices. Considering an example that Sx, y, considering S59, here it goes from the 5th row to the 9th column and it replaces in the next matrices. The next step, shift rows. It is a circular byte shift in each row. First row is unchanged. Second row does 1 byte circular shift to left. Third does 2 byte circular shift to left. Fourth does a 3 byte circular shift to left. Decrypt inwards using shift to the right. Since the state is processed by columns, this step permutes bytes between the columns. So we will go to the diagrammatical representation. So as I've said earlier, this is in 4 by 4 matrices where first row remains unchanged. In second row, it shifts to the 1 byte, where it shifts to left side, as we see, it is S10, S11, S12, S13, and it is shift to the left. So it is S11, S12, S13, and S10. Similarly for row 3 and row 4, it is being shifted. The next step is mixed columns. Each column is processed separately and each byte is replaced by value dependent on all 4 bytes in the column. Efficiently, matrices is multiplication in GF using primary polynomial. Considering a random matrix, we get this matrix. So here is a matrices. So it is multiplied with a random matrix, that is this. Each column is multiplied with this matrices and get n column, and which is sent to the first column of a new matrices. Each column again it is multiplied by these matrices and we get the new column, and which is inserted in the new matrices. So this is the diagrammatical representation of mixed columns. Expresses each column of the new state as 4 equations. One equation is to derive each new byte in column. Decryption requires use of inverse matrices or matrix with larger coefficient, hence it is little hard to have an alternative characterization, that is each column of 4-term polynomial with coefficient and polynomials multiplied by module x raised to 4 plus 1. The next step, add row key. Here we have to XOR the state with 128 bytes of round key, again processed by the column through efficiently a series of byte operation. Inverse for decryption identical, since XOR own reverse inverses with the reversed keys, designed to be as simple as possible. So we will go to the diagrammatical representation. As we see the 4x4 matrices where each column is XORed with the word and we get the new matrices. Hence this step is repeated as we get word 1, word 2, word 3. So AES key scheduling, it takes 128 byte, which is 16 byte key, and expands into array of 44, that is 32-bit words, where we can see word 0, word 1, word 2, word 3, where G is a function, which is where word 3 is XORed with G and we have got W4, a new word, where W4 is XORed with W1 and we have got W5. Same step is repeated for the further processes, that is W5 is XORed with W2 to get W6. Then W6 is XORed with W3 to get W7. For decryption in AES, we know that it follows same steps as above but in a reverse manner, where it is defined to be an equivalent inverse cipher with the step as for encryption but using inverses of each step with the different key scheduling. And this is the diagram where cipher text is converted. It has an add row key which is 40 to word 43, which goes to inverse of sub bytes, inverse of shift rows, inverse of mixed columns, add row key. Then it is repeated till 9 rounds, and in the last round we have only 3 steps, that is byte substitution, shift rows, round key. Now talking about mode of operations, there are 4 mode of operations. The first mode, electronic code block. Here plain text M is divided into n blocks. Each block is encrypted separately using the permutation FK to the generate ciphers. Here is the diagrammatical representation where we have a sentence which is known as M, which is divided into M1, M2, M3 to get an cipher, where M1, which is encrypted, and we got C1, M2, which is encrypted, we get C2, and then M3. So here the electronic codebook is fast, but it is not as secure as the other mode. It supports a parallel encryption and decryption, where the disadvantage we know is duplicate the data in plain text will be reflected in the cipher text. Now the second mode, cipher block chaining, where we have converted M plain text into blocks of M1, M2, M3, and where we have a random initialize vector where we have to XOR with each M to get an ciphertext, where we can see that this initial vector is XORed with the M1, and we have to do an encryption and we get cipher. The encryption line or the code is the next initial vector for XORing with next M2. Same the step is repeated over here till we get all the cipher. Advantage of this cipher is it supports all parallel computing. The duplicate data in plain text will not be reflected in the ciphertext. Next, output feedback mode, where M is also again divided into M1, M2, M3, so on till Mn. It has an initial vector which is passed to Fk. So here the initial vector is encrypted and we get the answer, and then the encrypted answer and the M1 is XORed to get the cipher. And where the encrypted answer is continued to encrypt with another encrypted answer, and we get M2 and it is XORed with C2, the key. So on we get it's the continuation till we get this. It has no padding, can prepare encryption decryption in advance. The disadvantage is it does not support the parallel computing. Next mode is counter mode, is where we have to increase a counter in each operation, in each this, where we have to initialize a counter and we have to increment a counter by +1, then we have to encrypt it, and M1 XORing with the encrypted code we get cipher. But it is not connected or interlinked with each other. We have to get a particular cipher by increasing the counter number. Where the advantage of this is it can prepare encryption and decryption in advance, supports a parallel computing, it has no padding. So here was the theory of AES. Let's go for manual. As we know, there are 6 steps where we have to choose the mode of operation. Then we select the key size, plain text, key text, initializing vector, that is 4 or IV. Then for which mode we are using, we have to use accordingly the IV, and the counter for only counter mode. Step 3, where it is necessary to we have to XOR in each mode. And step 4 is for the encryption mode, that is AES. Step 5 is fill the plain text in hexadecimal field with appropriate value in accordance with chosen mode of operation, and click on the encrypted button. And step 6 is the final encrypted text where we have to check the answer. Now the experiments, we have to choose a mode. I am choosing mode PCB. Will generate a new plain text key, and as we know, PCB doesn't require any CTR or IV, and as it is 128 bytes, so we have to do each row that particular key. Now we don't require XOR as well, we will do the encryption because there is no need of XOR in this diagram. So we'll copy this as a plain text, and key will be the same for the whole plain text. Encrypt. So here we required an pad where it's easy, so we can't get jumble in it. We'll take the second, that is M2. Encrypt. Now we'll take M3. Encrypt. M4 with the key encrypt. and the last M5. Encrypt. Now let's check the answer. So we get the correct answer. Now we'll select the mode, as we are keeping the byte as it is 128. We'll change it. We'll take a key text, and we need here initial vector, as the diagram gives and it requires XORing of the initial vector and the plain text. Save the initial vector in the notepad. Now, as per the diagram, initial vector is XORed with the M1 to get. So we will take this initial vector here and the M1, that is column 1 of the plain text. Then we'll get the XORing. Key is required, so we are taking the key as it is and the XORed answer as a plain text, and we are going to encrypt it. So here we get the first C1, so we'll paste it over here. This is our initial vector, this is our C1, and here we know that encrypted answer is the next IV XORed with M2. Now encrypted answer, that is ciphertext, is the next IV, as we pasted IV here, for the new M2 XOR encrypt. So this is what we get, C2, taking a ciphertext as it is, M3 XORing this is ciphertext 3. We'll take it here. It is ciphertext 4. So here we get the last cipher. Let's check the answer. Yeah, here we get the correct answer. Output feedback. Here it is initial vector, which has to be encrypted with the key, and the key is XORed with the M1 to get C1. So let's start. Output feedback. So as per the diagram, we will store this. Initial vector is encrypted. So initial vector as a plain text, key as it is, encrypted. And after encryption, we have to XOR with M1. So we'll paste here M1 XORing. This is C1. So remember, we have to not take C1 as an next vector to encrypt it. We have to take the encrypted one, that is this one, again to encrypt with it. So now we have to paste this as it is. Encrypt. We'll take this ciphertext, the next M2 XOR it. We get C2. Now taking this as the plain text, encrypted. XOR. We have to continue it till we finish the MN. Last one. The last cipher. So we get the correct answer for the output feedback as well. So now let's continue for counter mode. So in counter mode we have to use CTR as a counter. As shown in the diagram, we have to store CTR for CTR as it is. That is this. Next we have to increment in CTR. We have to change it. We have to do an encryption CTR with a key. That CTR is a plain text, key is as it is a key. Encrypted. After encryption we have to XOR the encrypted answer with M1 and to get the cipher. That is encrypted answer So here we get the XOR, that is cipher. So now we'll change the CTR, copy, which is again encrypted with the key. M2, change the CTR, change the CTR, So here we get the correct answer. Let's go to quizzes. So what is ECB stands for Electronic Code Book. Among of this CPA, which is not secure, this is CFB, and which of the following is a block cipher, all. For further readings, you can use or prefer this links for extra notes and all. So thank you. Here I sum up all the information regarding AES and modes of operation.